Okay, remember that a function is exactly equal to its Taylor polynomial plus the remainder. As n goes to infinity, the Taylor polynomial becomes the Taylor series, or the Maclaurin series. And that is exactly equal to the function if, as n approaches infinity, the remainder, or the error, approaches 0. So if the remainder goes to 0 as n approaches infinity, then the series converges to the function. All right, the instructions on this problem said, prove that the series converges to the function. So we just need to show that the remainder converges to 0 as n approaches infinity. So to do that, we're going to use the Taylor remainder theorem. Recall that this seems complicated, but it just comes from the Taylor polynomial formula, whereas the nth degree Taylor polynomial stops after the nth degree term. The first unused term would be the n plus 1th degree. So the n plus 1th derivative, x minus c to the n plus 1th power over n plus 1 factorial. Well, this problem number 13 is Maclaurin, so it's centered at 0, so c is 0. And the difference between the Taylor error bound and the Taylor polynomial formula is the c and the z. This z just needs to be somewhere between the x value that we're putting into the function as input and the c value where the function is centered. So we're looking for the maximum n plus 1th derivative for some value between x and, in this case, 0. Well, for this problem, the function is e to the negative 2x power. So we need to figure out what the possible maximum value is for the n plus 1th derivative of f. So what are some successive derivatives of f? There's f prime, there's f double prime, then f triple prime is negative 2 to the third e to the negative 2x, the fourth derivative. Again, the derivative of e to the negative 2x is just e to the negative 2x. And then using the chain rule, we have this constant of negative 2 to the thirds, but the derivative of this is negative 2. So negative 2 times negative 2 to the thirds is positive 2 to the fourth. And so we've established that the nth derivative is going to be alternating. So we could have a negative 1 to the nth power. That's a power of 2. And e to the negative 2x. So the n plus 1 derivative will be negative 1 to the power of n plus 1 times 2, oops, this is supposed to be an n right there, so 2 to the power of n plus 1, e to the negative 2x. There's the n plus 1th derivative. All right, at this stage, remember, this is the maximum error. We want to know what that maximum error is as a limit as n approaches infinity. It's really important to remember here that we're talking about x being a fixed value. So when we drop an x into this function, this series we think might converge to that function. And for that specific x value, x is fixed. So in this expression, x is fixed, and we're taking the limit as n approaches infinity. So as n approaches infinity, the maximum error is this expression. But remember that x is fixed, so we have e to a fixed power, a fixed base to a power of n plus 1, and a fixed base to a power of n plus 1. So the only thing that's changing then is n, the exponents, and this base here. So in the numerator, we're going to have a power function times a power function divided by, this is just a constant, and then a factorial function in the denominator. But we know that factorial functions grow faster than power functions, or even faster than products of power functions. Therefore, this limit is definitely equal to 0, and we're done. We've shown that the series for e to the negative 2x certainly converges exactly to the function e to the negative 2x.